So our next concept is DC distributors. Distributors means we are already defined. Distributor is a conductor which can delivers current from distributing transformer to the street poles. Is it? Distributors are the conductors. Is it? So that means a distributor fed the supply from secondary winding of the distribution transformer to the what happened our pole towers. Is it? That's why here loads are connected. For the on this distributor, loads are connected. Now we will do the calculations of this distributor, especially DC distributor calculation. While the distributor carries a DC supply, DC, we will make some calculations here. If the loads are connected at one end or both ends, when the loads are concentrated and when the loads are distributed. Now we will discuss the performance of DC distributor with different types of loads. So here in the DC distributors, for this DC distributors, the classifications of DC distributors are made on the basis of the feeders, on the way of connection of distributors for the feeders. Is it okay? So that means here, actually, not only for this way of connection of distributor for the feeders, the type of loads connected to the distributors also we can classify this distributors. Here, depending upon the type of loads connected to the distributors, the DC distributors can be classified as first one, distributor fed at one end. Second one, distributor fed at both ends. Third one, distributor fed at center. So that means here, depending upon the load connections of distributor, we will classify. In the loads again, concentrated loads are there, distributed loads are there. Now we will say first one, DC distributor fed at one end, concentrating load. Concentrator loading means the loads are concentrated on a particular point of a distributor. Is it? That means compulsory we will calculate the voltage drop at that particular point of concentration and power loss at that point also. Now see here, ma. This figure shows a two-wire DC distribution. Second wire is closed one, closed loop, return path, return conductor. AB, this is a conductor AB or a distributor AB fed at one end here. Is it? Faders are fed at one end. Here this is the fader or simply fader voltage, whatever it may be. This is fed at one end. And here having concentrating loads I1, I2, I3, I4 are the concentrating loads tapped off. Here the loads are taking power supply from the distributor. That means this phenomenon is called a tapping. That means a tapped off at point C. The load 1 I1 is at point C. The load 2 I2 is at point D. Load 3 I3 is at point E. Load E I4 is at point F. So that means here, what happens here means now see here now. Here, this is a total length of the distributor AB. This is a section of AC. This is a section of CD. This is a section of DE. This is a section of EF. This is a section of FB. Now, if we can observe here, these are nodes. A is a node. C is a node. D is a node. E is a node. F is a node. B is a node. Here, C is a node means current division takes place. D is a node means current division takes place. F is a node means current division takes place. B is also. So that means current division takes place means here this is a total current actually. This total current can be represented with I1 plus, I2 plus, I3 plus, I4. This total current is in between section A and C. Is it correct or not? By applying KCL, this is this current. And now When this current flows through in this direction, this is I1, this is the total current, this is IAC current. IAC minus I1 gives ICD. Is it? IAC minus I1 minus ICD gives I2. Due to this procedure, during this procedure, we can calculate the current in each section. Now, if we can observe here, R1, this is R1 is the resistance of this section. R2 is the resistance of CV section. R3 is the resistance of DE section. R4 is the resistance of EF section. Is it? So now here what happened here? Current is there. In this section, current is there. Resistance also there. Now we can calculate, we can find out the voltage drop across section AC, across section CD, across section DE, across section EF, across section FB. Now, not only voltage drop, the current through this section AC square of IAC square into the resistance of this section R1 gives the power loss in this section. That means during this sections we can calculate the total voltage drop across this AB distributor, power loss through this AB distributor by applying simple KCLs. Is it? And by applying simple KVL or voltage division rules, we can determine the voltage across this total AB distributor like this. See here, current fed from point A, simply I1 plus I2 plus I3 plus I4 as we discussed. Current in section AC, same I1 plus I2 plus I3 plus I4. Current in section CD, see here, CD, what happened? So I2 plus I3 plus I4. Current in section DE, see here, what happened? I3 plus I4. Is it? CD I2 plus I3 plus I4, DE I3 plus I4, EF I4. Then finally voltage drop in section AC. I am already told that. Current into resistance of that section. In AC current is I1 plus I2 plus I3 plus I4 into its resistance is R1. Its resistance is R1. That's why it is drop. Voltage drop in section CD R2. That's where that section resistance into current. Voltage drop in section DE. That section resistance into current. Voltage drop in section EF. That section resistance into current. Is it? Finally, the total voltage drop across distributor AD AB, the voltage across distributor AB is algebraic sum of the drops of each section. Is it? The sum of these voltage drops gives the voltage drop across AB or voltage across distributor AB based on the total voltage drop like this. Is it? It is easy to see that minimum potential will occur at a point F, which is the farthest from the feeding point A. Why minimum potential means length increases? What happened here? Voltage drop is more. That's why only minimum potential is just at the farthest end, far end, final end. Is it? So based upon this particular concept, we will do a simple problem. That is, see, a 2-wire distributor cable AB is a 2 km long and supplies load of 100 amperes, 150 amperes, 200 amperes and 50 amperes, situated 500 meters, 1000 meters, 1600 meters and 1200 meters from the receiving from the feeding end points. Each conductor has a resistance of 0.01 ohm per 1000 meter, that is 1 kilometer. Calculate the potential difference at each load point section. Load point means a particular point the load is tapped off. Point means concentrated. Calculate the potential difference at each load point if potential difference of 300 volts is maintained at point A. So now given data is, first one, Length of AB 2 kilometers is given. Next, resistance of each conductor 0.01 ohm per 1000 meter, but it is converted into meters also. Meters also. Next, we can go for the figure here. AB based upon the data, we can discuss that. See here. 2 kilometer long supplies a load of 100 amperes per 500 meters. 150 amperes per 1000 meters. Next, 550 amperes. See here. 100 amperes, 150 amperes. This is section having 50 amperes. So next in the given data, 1600. Next 600. For the next 600, 200 amperes. See here, 200 amperes. That means for the this one having 50 amperes. And for the next section, for 2000, next 400 meters, what happened? It is 200 amperes. Like 250. Like this. Then after that, it is 50 amperes. After that, it is 50 amperes. Is it? So totally, how much current takes place here? 100 plus 150 plus 200 plus 50. 150, 350, 400. Is it? So that's why total current is like this. Now first we have to calculate resistance first. We would have calculated the voltage drop. So see here, 500 meters. This is 500 meters. In the given problem, we have resistance of each conductor is 0.01 ohm per kilometer. So for per meter, first we can calculate. Per meter means into 1000. Sorry, divided by 1000 we will substitute. So that means per meter here 0.01. So resistance per 1000 meters of distributor is 2 into 0.01 means in the given problem one conductor is there. For one conductor is given, for two conductor loop resistance we will calculate. That's why 2 into 0.01, that is 0.02. And per meter 0.02 by 1000. And this section AC having 500 meters into 500. Then 0.01. So like that resistance. First observe here. First per meter we can calculate. So first 0.02 for loop conductor for this loop conductor. This section, so simply loop conductor. Per meter is 0.02 by 1000. That is per meter. But for 500 meters into 500, 0.0 in this section. Next, in this section, 0.02 into 500 by 1000. In this section, into 600. In this section, into 400. That means this is the resistance. Now coming to the current, IEB. See here. IEB here, 50 amperes. IDE, 250. ICD, 400. IAC, 500. Like this. Like this, we can calculate it here. So that means simple case here. ICD, IAC. IAC means what happened here? In this section, 500 amperes is there. 500 amperes means this is the total current. Means 100 is there, 150 is there, 200 is there. Is it right? So 150, 150, 200, 200, 200, 400, 400, 100, 500. Is it like that? In the previous class, in the derivation, what I told, same procedure we can apply. Then we can calculate easily the section currents. If section currents are determined, already section resistances are determined. Then product of current and resistance is called voltage drop across the section. Then the potential difference at load point C. See here, this is the load point C. The potential difference is AC. That means we see voltage at A minus potential of voltage drop in AC. Simply, you want to calculate potential at this C, and this is VA. Simply what happened? VA minus VC is equal to VAC. But we want potential at point C. That's why VA minus VAC is equal to VC. VA is already given 300 volts. VA is already given 300 volts. Is it right now? So now VAC we have to calculate. Current in the section 500 ampere is there. Resistance is there 0.01. Then now we can easily calculate VC like this. Simple voltage division principle. Like this. 300 minus 500 into 0.1, 295. Next, potential difference at load point D. Same principle. VD minus VC VD minus, that means VA minus VD, or potential difference at load point means VC minus VD is equal to VC minus VD is equal to VCD. From that, VD is equal to VC minus VC, 290 volt. Then potential difference at point E. Simply VE minus VD minus VDE is equal to V. Simple voltage like this. Potential difference at load point B. Like this we can calculate. Like this we can calculate the potential difference. This is a simple problem based on the when fader can fed at only one end. Fader excitation can fed at only one end, and these are concentrated loads. These are concentrated loads. So the next concept is uniformly loaded distributor fed at one end. Uniformly loaded distributor means we are providing uniform loads, not non-uniform loads. Uniform loads at the each section. So see here, shows the single line diagram of two-wire DC distributor AB fed at one end A, and loaded uniformly with I amperes. Loaded uniformly. Uniformly means the same current, same load. But in the previous case, concentrated loads, same voltage is not, same current, same load is not provided. But here uniform is the same load with I amperes per meter length. It means that every L meter length of the distributor, the load tapped is I amperes. Let the L meters be the length of distributor and R ohms be the resistance per meter run or per meter length. Then we have to calculate the voltage drops. Now see here, consider a point C on the distributor. This point C on the distributor at a distance of X meters. See here, this point C is the X meter distance, but the total length or distance is L meters. Is it? So now, then current at point C. See here. So for the total length, the current is capital I. But the point C is located at X meter distance from point A. Then we have to calculate the current at point C. In order to determine current at point C means we can subtract the current remaining portion, the current at remaining portion. That means L minus X portion. Is it? That's why IL minus IX amperes, the current at point C. Then I into L minus X. Current means the load tapped at point C. Is that current means the load tapped at point C is I into L minus X. The load is tapped at where the distance is in the total length of L meters. We can subtract X meter. In that length, the current is there at point C. Now consider a small length dx and near point C. Its resistance is RDX. Resistance is RDX, and voltage drop is nothing but current into resistance. Resistance is RDX. Current is I into L minus X. Then what happened? IR into L minus X dx. This is the potential difference. Then total voltage is equal to integration will be like 0 to X IR into L minus X dx. Then IR into integration for L dx, Lx minus X dx, X square by 2. So then if by putting X is equal to L, then what happened? IR into L minus X, L square by 2. X is equal to L. Then L into L means L square minus L square by 2, 2L square minus L square by 2. That means L square by 2. That means IR into L square by 2. That means half IR L square. So that means half IR L square means IL into R. I into L means the current throughout the length, that is capital I, we are already discussed. And R into L means the resistance throughout the length, that is capital. Is that right? That's why the voltage drop throughout the distributor AB is 1 by 2 IR if it is a uniform distributor. Is it right? Then IL is equal to what happened here? IL is nothing but what happened? Total capital I. Is that the total current entering at point E? R into L means resistance, total resistance of the distributor. Now see if any problem is there. Again, if there is no problem in my slide, next we will discuss. So see here, there is no uniform loading. This is also concentrated loading. So then, if you can assume the uniform loading, you can do the same procedure. Voltage drop means the formula we are discussing as usual, isn't it? That is 1 by 2 I into R. I means total current, resistance means total. If total current is not given, we can calculate. Is that right? Uniform is you can add that. Is that right? You add that means simple case. Resistance also add that, then you can do that. So next one. Distributor fed at both ends concentrated loading. Here in the previous case, distributor can fed at only at single ends. But here distributor fed at both ends. And here loading is concentrated loading. That means tapped off on a particular point here. See here. Whenever possible, it is desirable that a long distributor should be fed at both ends instead of at one end only, since the total voltage drop can be considerably reduced without increasing the cross section of the conductor. That is the main advantage of when distributor is fed at one end. Both ends. Voltage drop can be reduced, is it? Without increasing the cross section of the conductor. So here in this case we will discuss two cases, that is with equal voltage and with unequal voltage. Two ends means the distributor fed at two ends means feeder serves for two ends. That means what about the voltage of feeder? Maybe equal, maybe unequal. So in these two cases we will evaluate the voltage drop and power loss. So see here, this is a distributor fed at so here this is equal voltages. This is one end, this is one end. Here loads are tapped like this. That means if we can observe now, what happened here it is. This is a common point. Due to this voltage excitation feeder, the currents enter in this direction. That means X shows the current flow in this direction. And due to this voltage excitation, the current flow in this direction. That means like this. That means at this common point for these two voltages, what happened? The current is added. So like this basic principle, we can derive all those things. Potential of minimum potential. Potential, point of minimum potential. Where the minimum potential is exist, far end minimum potential is exist. For this excitation, this is far end. For this excitation, this is far end. So that means minimum potential is exist at that point. That's why here we can see I3 is equal to Ix plus I, or simply that is IE. It is a point of E. At this point of E, Ix plus I. At this load tapped is I3 is equal to Ix plus I. And we can evaluate the point of minimum potential. See here. See here. I1, I2, I3 means concentrated loads, not uniform loads. So for this, simple case here. IA is equal to I1 plus I2 plus I3. So IAC is nothing but IA. Then IDE in this section current. What happened? IA minus I1 minus I2. Simple case here we can apply. Is that no problem in that? So that means if we can come into this side, first individually we can observe it. ICD, what happened here? IA minus I1. IEB, what happened up to here also? IA minus I1 minus I2 minus I2. Simple case here we can apply that. So then voltage drop, current calculation is similar. Voltage drop between A and B is nothing but simply we have the formula. At A voltage is V, at B voltage is V. That means voltage difference means VA minus VB. The voltage at VA at point A means V. The voltage at point B means V. That's why V minus V. V minus V. Then what about currents? The current is like this simply. The current is IA. Then IA minus IA. I1. The currents, the total current flows through this distributor AB. IA plus, ICD plus, IDE plus, IAB. IDE means IA minus I1 minus I2. IAB means IA minus I1 minus I2 means I2. Like this. IA into RAC. RAC means the resistance of that section. IA minus I1. IA minus I1 means that is IAC. So see, IA minus I1. ICD. IA minus I1 means ICD. So like that, by applying KCL simply. ICD. That's why RCD. Like this, the current through that section into resistance gives the voltage drop. So this is the total potential difference is equal to voltage drop across. Both are equal. So then, so if you know it is a constant value, it is a constant value. What happened here? This never constant. With equal voltage means what happens? Zero it is. And it's zero. Then what happens? Simply from this we can calculate the potential difference or simply potential across that distributor simply. If potential is known value for power loss in each section, IA square RAC, IA minus IA1 square RCD, IA minus IA minus I1 minus I2 square RDE, IA minus I1 minus I2 minus I3 square REB plus RR plus. That's why there is a power loss through that distributor. This is with the equal voltages. But for unequal voltages, what happened here? Unequal voltages. Simply same equation. But here what happened? Unequal, some constant value applied. There are some constant value applied. Is it? So like this we can calculate that. See, V1 minus V2 voltage drop over AB. Remaining analysis is as usual. Current drop through. That means this analysis is the same. This equation is the same. Is that right? From that we can calculate